Now, if you're an engineer or if you've taken physics, it's important to note that this is different than what you learned previously. In geology, compressive stress is the positive number. Tension is a negative number. The reason that in geology compression is the positive stress is because in the real world, in nature, that's what's common. Compressive stress due to gravity is the most common stress you'll ever encounter. Therefore, it's been designated as the positive value. Tension is much more rare. Tension stress gets the negative value. Now, two terms that you'll see tossed around quite a bit are isotropic and anisotropic. When we're talking about stress, isotropic stress means that it's the same in all three directions. Sigma 1, 2, and 3 are equal to each other. Anisotropic, just the opposite. They're not equal. Now, a couple of other terms are, triaxial stress, where you have all three. It's anisotropic, and none of them are zero. Biaxial, you have stress in two directions. In one direction, it's zero. Uniaxial, you have uniaxial compression. Compression in one direction, the other two are zero. Uniaxial tension. Tension in one direction, the other two are zero. Think of a weight hanging on a rope. That rope has uniaxial tension. It's tension straight down due to the mass of the thing on the rope and gravity pulling on that mass. There's no tension in any other direction. So sigma 2 and 3 are zero. Sigma 1 has a negative value of whatever the mass times gravity is. That's the force on it. Uniaxial compression would be you set that same mass on the top of your desk. There is compression down on your desk, but there's no stress being applied in any other direction to your desk. So it's uniaxial compression. Hydrostatic pressure is equal in all directions, so it's isotropic, and it's what's experienced if you go underwater. Thus the term hydrostatic pressure or hydrostatic stress. And it is very important that you remember it's equal in all directions. It's isotropic. Now this little diagram here is going to show up quite a few times. This is something, you probably want to even have a copy of this that you print out somewhere to reference or flip to the page in your book. These kind of experiments can be done with clay blocks, wax blocks, or even with rocks. A lot of uniaxial compression, just compressing from the top and bottom, are done to check rocks for their compressive strength, or to check cement or plastic or other materials, how much stress can they take before they break. And when they do break, they're going to break on a plane. You can see it over here in the actual drawing of the clay block, and you can see it here in the little cartoon drawing. It's where the displacement happens, where it completely fails all the way through. Now there are other cracks that start in different orientations, but the one that breaks all the way through and then things slide, which relieves the stress, is the fracture plane. And that's a key important term. That is the fracture plane. Now, sigma 1, the stress that we applied to the top, the greatest stress of all, in this case the only stresses from the sides are atmospheric pressure, incredibly minor. But from the top, we're applying lots of stress so we can break our clay, and we can decompose that stress into the component that's normal or perpendicular to the fracture plane, and the component that is parallel to the fracture plane, the shear component. This theta down here is important that you keep track of what angle is theta. This opposite angle here, it's a different angle, often called phi. But the only time those two angles will be equal is if the shear, or if the fracture plane happened to be at 45 degrees to the sigma 1. Almost never happens. So keeping track that theta is the angle between the fracture plane and the perpendicular surface that sigma 1 is being exerted on. We can do lots of geometry to figure out what the shear stress and the normal stress are equal to if we know sigma 1 and sigma 3. But that's not a lot of fun necessarily, to be constantly punching in these cosine and sine equations into a calculator. It'd be wonderful if there were an easier way, right? Well, before we get to that easier way, just a quick little recap. Normally in an in-class lecture, that would be the end of the first lecture, and then this recap would be the beginning of the next one. But I'll be able to just keep going straight through right now. Key things. Sigma 1 is the largest stress, sigma 3 the smallest stress. Occasionally, if you're reading literature from a long time ago, or from another country, or from somebody who's not really a geologist but is working on a geology project, you might see sigma 3 and 2 switched. But the convention in the textbook, the convention in this class, the convention in most geology in this country is that 3 is the smallest. Sigma 1 is always the largest in all the conventions I've ever seen. Shear stress is along the plane, and it's going to cause shearing of an object. Kind of like rotating parts of it around the central point. If you have a stack of playing cards or stack of paper or even a textbook and you exert force along the side, you can see it shearing into a shape like this. The dotted line showing the original square shape. The shear stress is called gamma. It's this Greek letter that looks kind of like the letter Y, and it's equal to the tangent of the angle between the original shape and the new shape. Now, we will definitely cover this more later, but that's what shear stress is. We have 9 components of stress on any object. We can simplify them down to 3 because xy and yx, for example, are in the same direction. They're parallel to each other. Either one of them is bigger and there is a net shear stress, or they're equal and there's no net shear stress in that line, in that direction. So we can simplify it down to 6 components. If they cancel out, shear stress is 0 and the body is at rest. This means, the rock in the ground is stationary. It may be getting compressed, it may not be, but it's not moving. Because if there's shear stress, it's moving in some way. It may be moving from one place to another, it may be rotating, but there's definite movement.